When we deal with probability of seeing one event or another, we end up using addition. So a key word we want to look for here is when they describe some event, and then connecting between them would be the word or. And with probability and with statistics, like I mentioned in previous videos, when we say or, it means one event or the other or both. And this or both scenario is sometimes there and sometimes not. So we're going to have kind of two variations of our rule here. In fact, I'll draw a line to separate our page. What we're going to see is the rule changes for disjoint events versus non-disjoint events. So we'll talk about how we can see that from the problem, how we know whether it's disjoint or non-disjoint, and how that affects the calculation. Now, we've actually looked at this disjoint scenario already, but let's look at one more example with it. So we have our 10 jelly beans that we've been working with. We're drawing one jelly bean, and we want to see what's the probability that it's purple. And then there's our connecting word of or, red. So in terms of notation, I write probability of purple, or red would be the connection. And then intuitively, looking at the outcomes here, we'd have our 2 purple jelly beans or our 4 red jelly beans. So there are a total of 6 jelly beans that fit this scenario out of the 10. But the breakdown of it and the calculation and how we're thinking of that and how that's interpreted is we are taking how many purple jelly beans plus how many red jelly beans. So it ends up being this addition. Like I said in the previous videos, this is the mathematical rule, but if you can think of it a different way, you're welcome to interpret. I mean, you have to get to the same solution, but there are other ways of thinking it where you can end up with the same fraction, same decimal, and the same conclusion. So in terms of using the formula, we'd have 2 out of the 10 plus the 4 out of the 10 red, which would be a total of 6 out of 10, which is 0.6. So we'd say something like there is a 60% chance of drawing a purple or red jelly bean. Now, this case, in terms of our definition of or probabilities of one or the other or both, well, we could think of we have purple or red, but we don't have that both scenario. And that's what makes this disjoint. Is that for the setup of this case with our jelly beans, it's only one color or the other. There's no overlap of colors. So with that, it being disjoint, we would use this rule where we just add the separate probabilities, just like we did up above there. Another word that you might see for disjoint come up is mutually exclusive. Those mean the same exact thing, but just means if they're disjoint events, there's no common outcomes. Can't have both. So let's look at a scenario where we see a difference between disjoint and not disjoint. So this is some data that was collected. We have a two-way table here, or contingency table, where they did a treatment for cocaine users. So they get desipramine to one group, lithium to one group, placebo to another, and then they recorded whether or not they relapsed. So with the first question here, what's the probability that they were given desipramine or lithium? Now these two groups, I'm just going to highlight it on the table. So here's our desipramine group. Here's our lithium group. There's no overlap between them. They don't intersect anywhere. There's not going to be someone who is taking both treatments. All the people in this group had one treatment. So with that, this would be a case of disjoint, like we saw up above there. So we're going to use addition, and I'm always going to mark that. Whenever I see or, I always put a little addition symbol so I know the calculation to use. So with this, if I want the probability, if they were in the desipramine group or lithium group, we're going to add those probabilities, and it's just direct addition like we did up above here as the rule specified. So despermine group, there were 24 people in that group out of the 72, plus for the lithium group, there were 24 people out of the 72. And you don't need to show any simplification in terms of fractions, just plug this into a calculator of some sort and get a decimal out. So with this, we would say there is a 66.67% chance they were given despermine or lithium. Okay. Now let's compare that to this next scenario. What's the probability that they had lithium or relapsed? So lithium group, this row right here. Relapse group is this column right here. Now you'll see this like in part A where we saw they were disjoint. It was because they were both rows. They were kind of running parallel to each other. Same thing if I had used relapse or no relapse. If it was both columns, that would also be disjoint. But in this case, where we're mixing columns and rows with each other, we're going to end up with an overlap. We have these 18 people that were both taking lithium and relapsed. So with this, where we're going to be using our addition rule, we need to keep in mind that this is not disjoint. It is possible to have both. So with that, let's see how our rule changes. So we're looking for this probability of lithium or relapsed. Now, if we kind of go the route of our old rule, what we would be doing is adding our probabilities. So we would take how many were in the lithium group, 24 out of the 72, plus, sorry, my 7 got a little weird there. All right, plus the relapse group, which there were 48 out of the 72. So if we didn't change anything as of right now and put this together, the solution we would get out would be 100%. But from our table, seeing all these other possible treatments and also this case of not relapsing, there isn't a 100% chance that they were taking lithium or relapse. This is incorrect. And sometimes even when you do this, it might go over 100% and make it really clear that something went wrong. So let's talk about what's happening. So when we did this, and I'm going to actually re-highlight what we did up here, we took everyone who's in the lithium group. So those 18 people that relapsed and those 6 people that did not relapse, so a total of 24 people. And then what we did is we added in the people in this group, 10, 18, and 20. So we had those 48 total people. When we add those numbers together, when we add that 24 and that 48, what ends up happening is these 18 people, they were counted twice. So we're getting too many people as part of this group. Because what it would really come down to in a broken down sense for our numerator, we'd have 10 plus 18 plus 20 plus 6. That would really cover all the groups. But if we're using these totals in the margins, if we just use those totals, that intersection, that overlap of the two, gets double counted. And that's a property of them being not disjoint, is that we have that overlap. So if we just add them, it's adding too many. So what we're going to do is make up for the fact that they were counted twice by subtracting them out of there once. And then we'll have everything counted exactly as it should be. So what I'm going to do to my formula down here is where I'm adding the two probabilities, I need to subtract the intersection of the two by taking the probability of that they were taking lithium and relapsed. So both of those characteristics. Because then what that will look like is the intersection of the two, so the 18 out of, and I realize I wrote 27 there, but it should be 72, sorry about that, out of 72. This is our complete formula that will get us exactly what we want to calculate. So if we plug all that into the calculator, it should end up being a 0.75, which is much more accurate. So we would just say there's a 75% chance they had lithium or relapsed. So this is what we want to do when the events are not disjoint or non-disjoint events. It's when you do have this overlap, so they can occur at the same time. And our rule turns into adding the two probabilities, but then what we need to subtract out, this little piece, is the intersection of the two. So where do those groups overlap? We need to subtract that out once, because by just adding those, we double counted a group. So with that, those are the two rules for addition when we see OR. However, what I want you to think about is they really are the same rule. It really does come down to just this rule. But when we try to use it for disjoint cases, like if we go back to part A up here, if I tried to subtract out the probability of both, so what's the probability of that they were taking desipramine and lithium, so both, it just turns into 0 when they're disjoint. You just plug in 0 because there's a 0% chance of that happening, and you'd end up at the same answer. So while it looks like two formulas, it really is just one formula for this non-disjoint events. It's just when they're disjoint, that intersection turns into 0.